and then you start.
Good morning, one and all. I, Sriram Mustapure, Assistant Professor, the Department of Civil Engineering, Sir MVIT. It is an honor to welcome all faculty participants for a fifth day of our FDP on Sustainable Construction Material Practice and Technology, organized by Department of Civil Engineering, Sir MVIT. Now, I would like to take this opportunity to extend a warm welcome to our guest speaker, Dr. Pranav Pradeep Kumar, sir. Now, I request Dr. Ravi Kumar, sir, HOD, Department of Civil Engineering, Sir MVIT, to welcome the gathering.
A very good morning to one and all for present as we gather here on the final day of our 5-day faculty development program on sustainable construction materials, practices and technologies. It's a very great pleasure that I extend a warm welcome to each and everyone and also a warm wishes to everyone on this World Water Day today. For the past few days, we have dwelled into the area of sustainable construction, exploring innovative materials, practices, and technological that hold the key to a more environment-conscious future. From eco-friendly building materials to energy-efficient construction material, we have gained valuable insights that will undoubtedly shape the way we approach construction years to come. Throughout our journey we had a privilege of learning from esteemed experts in the field, engaging in enlightening discussion and exchanging ideas with fellow educators and professionals. I hope everyone accept this. All the participants, 70 participants now who have logged in, will accept this. Before we wrap up the program today, let us reflect on the knowledge gained and the connections made and the inspiration received. With this note, I welcome our today's distinguished speaker and our own alumni, Dr. Pranav Kumar, to today's session. It is my honor and privilege to have you here, Mr. Pranav. Now I request KVR Prasad sir to introduce the speaker of the day. Over to you, sir.
Please unmute yourself.
A very good morning to one and all. Sorry for that. I, KVR Prasad, Associate Professor, Department of Civil Engineering, take it as my honor to introduce our today's guest speaker, Dr. Pranav Pradeep Kumar. Dr. Pranav Pradeep Kumar is a highly accomplished researcher in the field of civil engineering, particularly focused on sustainability and structural engineering. Here is a summary of his academic and professional achievements. Dr. Pranav Pradeep Kumar achieved his PhD in civil engineering in structural engineering from College of Engineering, Texas AMU University. He obtained his Masters of Engineering also from the same university. He did his Bachelor of Engineering in Civil from Sir MVIT. He has achieved first rank in the civil engineering in VTU in the 2016 outgoing batch by receiving 12 gold medals. At present, Dr. Pranav Pradeep Kumar is working as a postdoctoral associate at the Concrete Sustainability of Massachusetts Institute of Technology, USA. His research interest spans various domains within civil engineering, including life cycle energy, carbon and water analysis, sustainable design of materials and structures, concrete composites, bridge engineering, fatigue and fracture mechanics, building information modeling, finite element analysis, reliability of structures, railway engineering. Dr. Pranav has already authored 12 international, he is having to his credit 12 international journal publications, 12 international conference proceedings, 5 poster presentations. Dr. Pranav Pradeep Kumar is also recipients of various awards. He has won Vanadium Award retrospective by the Institute of Materials, Minerals and Mining 2023. Best Paper Award issued by International Advisory Board in May 2023. Student Merit Award in 2016 awarded by Association of Consulting Civil Engineers India. Also Best Outgoing Student Award by the Department of Civil Engineering, SRMBIT. He is having membership and leadership roles like he is a Vice President of Structural Engineering Association of Texas, TAMU Student Chapter. He is Associate Member of the American Society of Civil Engineers. And Dr. Pranav Pradeep Kumar already achieved 87 citations in Google Scholar. He is having a research interest score of 119.5 on the ResearchGate. Dr. Pranav Pradeep Kumar's extensive academic background, research contributions, and professional affiliations reflect a strong commitment to advancing the field of civil engineering, particularly in sustainable infrastructure and structural engineering. With this brief introduction, I now take this my honor to welcome Dr. Pranav Pradeep Kumar, and I request him to present his today's lecture. Before that, a small announcement to all the participants. Before Dr. Pranav Pradeep Kumar starts his speech, we request all of you to kindly switch on your video so that we will take some group photos of all the participants, including Dr. Pranav Pradeep Kumar. We request all the participants kindly switch on your video and mute your speaker so that we will be taking group photos. Today we will be, as it will be the last day of our FDP, to have a memory with us. We want to have every one of your photos also with us. Kindly we request all of you to switch on your video, kindly mute your speaker. After that, Dr. Pranav will start the presentation. We also welcome so many of our alumni who are present today. We welcome everybody. We welcome all the participants. No need, no.
I changed the layouts.
Hello, Dr. Pranav. Can
Yes,
you
sir.
hear me?
Yes, I can hear you.
Yeah. Can you kindly start the proceedings now? You can go ahead. You can start your presentation.
I just shared my screen. Just wanted to check if it is.
Thank all the participants. Now you can switch off your video and kindly mute your audio also. All of you kindly mute video and audio.
Yes, sir. Is my screen visible?
Yes, Pranav, it's visible.
First of all, thank you so much, sir, for that wonderful introduction. Firstly, I would like to thank Ravi Kumar sir and Anita ma'am for inviting me to present today. Being an alumni of MVID Civil Department, I'm really honored and happy to be a part of this program. With that, I would like to welcome you all to today's session. Today, I'm going to share some thoughts on impact of design measures on material selection for a sustainably built environment. But before we get into the core of the topic, let me just put this out there. This is kind of to remind all of us that the big problem that we are facing in this century, as you may have already heard this maybe from the other speakers, is climate change and global warming. And with all spectrums and sectors across the globe shifting their gears towards reducing the global warming potential, or in other words, carbon emissions, it is extremely important for us as civil or construction engineers and researchers to think about this from every angle because our industry plays a significant role in this aspect. So with that thought in mind, let's think about how this word sustainability has stolen all the limelight across the globe. Today it is spoken everywhere. Everyone's getting involved in sustainability in some form or the other because it is a hot topic for the 21st century. So from a crude perspective, let's try and define two different cases here. One is a fully sustainable Earth, for which we probably have to go back several millenniums. And on the other end, we have a catastrophe waiting for us in the form of resource depletion or extreme climate conditions, polluted air, or water scarcity. Currently, we are somewhere in between these cases. And while it is impossible for us to go back to the fully sustainable era, it is clearly possible for us to ensure that we avoid this big danger that's ahead of us. While where we are today seems not too bad, but the scary part is not where we are today. The scary part is the speed with which we are moving towards the danger. And so the question is, why is this happening, or why are we thinking this is going to happen? So one of the key parameters here is urbanization, or cities. So currently, cities contribute to just 3% of Earth's land, but it is responsible for 75% of carbon emissions. And with the population expected to reach approximately 10 billion by 2060, which is in roughly about 3 decades, the building footprint alone is expected to double its current share. That is, it's going to add roughly 250 billion square meters of a footprint by 2060. Now, what does that do? It calls for more deforestation, and with all this translates to more and more carbon emissions, which is inevitable. It's only a matter of time that we're going to reach there. So at present, we can see that the construction industry consumes approximately 16% of the total global fresh water. It consumes over 40% of the total global energy supply in the form of embodied and operating energy, and over 90% of this embodied energy is attributed towards construction materials. The construction industry also accounts for about 40% of the total global carbon emissions, and steel and concrete clearly contribute significantly to the energy and carbon footprint of buildings. with steel approximately about 11% and concrete approximately 5 to 9% of the total global carbon emissions. So it is important for us to understand how material and design parameters influence its environmental sustainability. So having discussed this issue here, let's now dive into how we can mitigate this challenge. And therefore, let's look at this issue from a carbon, energy, water perspective. So a life cycle assessment, if we look into any system in general, in order to perform a life cycle assessment, it requires several input parameters such as raw materials, energy, water, and the system generates some outputs in the form of products, which could be byproducts or co-products, emissions in the form of greenhouse gas emissions or carbon dioxide emissions, as well as wastes that gets disposed, or in some cases, they get recycled and reused. So this is attributed to its entire life cycle from an extraction, production, installation, usage, and end-of-life disposal or reuse phases of a particular system or a product or a building. And therefore, it is important for us to account for not just the carbon and energy, which is quite commonly accounted for, but also to study the impact of another natural resource that's getting depleted, which is water. Therefore, it is important for us to look at this problem from a more holistic perspective, where the trade-offs between these aspects, between carbon, energy, and water, are considered and accounted for in all our modeling aspects. So in order to perform a life cycle carbon, energy, or water analysis, we could look into 3 different parameters. One is sustainable envelope or sustainable materials, and third could be sustainable design. So for today's presentation, I will try and focus just on the materials and design phase. So if we look into the materials, we can broadly classify them into, but not just limited to what I'm going to show in the following categories. We could define materials as new building materials or filler materials, a combination of 2 or multiple different materials, materials that enhance the properties of other materials. And from a design perspective, we could modify the design of a component or an element within a building or any other infrastructure, or interior design, or modify the entire building as a whole. So therefore, in order to conduct a holistic life cycle analysis, it is important for us to look into the entire flow of a commodity, starting from the product stage to all the processes that's involved in creating the product, as well as all the services that's involved in preparing this particular product. So with that, let's look into the first parameter, which is the carbon footprint. So the total emissions can broadly be divided into 2 categories, which is embodied energy, embodied emissions, and operating emissions. And we can clearly see from this pie chart to the left here that embodied emissions is significant in terms of carbon footprint. And in the right figure here, we can see an inverted pyramid, which was published by the World Business Council for Sustainable Development. It is a wonderful representation of what a carbon reduction strategy could look like. So from top down, we can see in the pyramid, it shows efficient and effective methods to achieve environmental sustainability. So clearly, the least efficient or effective method is to build nothing from now. But that's, as we know, is not possible. So moving down the line, building efficiently or minimizing the waste could be the best strategies that we can adopt. And these are some of the strategies that could accomplish this particular levels of carbon footprint reductions. So, and moving to the second parameter, which is energy. Similar to carbon, it has 2 major components, which is embodied and operating energy. But contrary to the carbon emissions, here the operating component is often more significant as compared to the embodied component. And it is also important for us to consider the impact of different energy source specific requirements during the entire life cycle of a building or a material. So the energy sources can broadly be classified into the 5 different classifications, which is oil and gas, petroleum, coal, natural gas, and electricity. And finally, the third parameter here is the water footprint. The embodied water includes the water consumed directly by the materials, the water consumed indirectly by the materials which is used for the production of the main material that we are looking into, and also a third component, which is energy-related water use, that quantifies the water consumed by different energy sources that was used for the production of the material or the product under consideration. So often the energy-related water is considered as part of the indirect water component, but in this study, what we thought was to consider the energy-related water as a separate component, because it would be important for us to decouple this use to identify the significance of water usage by different energy sources. So the significance of the energy water model can broadly be observed in this slide, where you can see on the left side, here is the contribution of the different sources for the generation of electricity. So that's just how we generate electricity. And this plot or this data is taken for United States. And on the right side plot shows the water consumption by these sources to generate electricity. So you may observe that here approximately 87% of electricity is generated by thermoelectric power plants, which uses 58% of water, while the remaining 13% of electricity that's generated using hydroelectric, geothermal, water, and wind requires 42% of the total water consumed for the generation of electricity in just the United States. And similarly, we can observe not exactly the same numbers, but similar patterns in other regions as well. So this clearly underscores the value of looking into not just an energy model, but also a coupled energy water modeling. So in order to determine the embodied carbon, energy, and water of different commodities, an input-output based hybrid model is used, which is developed using the recent US Census data. And the IOH model uses a macroeconomic data between different industries. And the economic flow, since it's an economic data, it's all in terms of economic values. So the economic flows are converted into water and energy flows using water and energy tariffs for different regions. And the CO2 emissions per fuel type is used to determine the embodied carbon. And the individual commodity unit prices, which is in dollar per kilograms, are used to determine the embodied energy, carbon, and water per unit weight. And some of the key features of this model includes that it's a complete calculation, because we have vast data on the macroeconomic side of the different industries, like how much money is invested in producing a commodity and how much money is obtained from selling these commodities as well. And since it is a data-driven model, it is very important for us to ensure that the data is complete, to ensure that our final results are reliable. And also this model, we have to keep in mind that we don't double count energy while transforming the economic flows into energy flows. And finally, it lacks temporal representation because it's a census data and it is not a continuous process. It's reported every 5 years in US, and in some regions it's every 10 years. So that's a drawback with respect to the temporal representation idea. So this slide here shows a schematic representation of how the energy and water intensities are calculated. So we start by exploring the different data sources. It could be energy usage or water usage data from different sources and for different industries. And from there, we then categorize it into broadly 9 different industry sectors, which is defined by the US Census Bureau. And the IOH model is then used to integrate the use and make data from the US Census Bureau, along with the energy and water information that we obtained for the different industries to generate the energy and water intensities per unit cost. So here we can see that the cost parameter is included within the energy and water intensity values. So in order to finally compute the embodied energy or the embodied water, which is the final stage of the modeling, it is important for us to use the aggregated or disaggregated building material commodities and the cost of these construction materials and or building as a whole, and combine the cost along with the energy intensities, which is in British thermal units per dollar, or if it's water, it's in gallons or liters per dollar. And once we combine these two, we would get the total embodied energy or embodied water that's associated with the material that we are considering or the building that we are analyzing. So the IOH model is implemented to determine the direct and the indirect embodied energy and the embodied water that I was talking about in a few slides back. So this plot here shows 12 upstream stages of indirect embodied energy and embodied water. And it is important to note here that this is showing only the indirect component, not the direct component. So all the 12 stages that you see here are the upstream usage of the production of the raw material of a commodity. So this doesn't include the direct emission, direct energy or direct water intensity for the production of a commodity. So clearly from this plot, we can say that there's higher indirect embodied water observed in the second stage as compared to the first stage, whereas the highest indirect embodied energy is observed in the first stage. So what this actually translates is, in the very first upstream stage, there's a lot of embodied energy that's being utilized, whereas with respect to water, it's always in the second stage or second upstream stage where we observe more of the water usage. So
यहीं पर एटीएम लेके हम आते हैं, यहीं रहो, यहीं पर रहो तुम लोग, हम आ रहे हैं एटीएम लेकर, हम आ रहे हैं, यहीं रहो तुम.
So for this particular analysis,
Pranav, can you please unmute yourself?
Sir, please unmute yourself.
hello, can you hear me now?
Yeah, we can hear.
Okay.
Hello, Pranav?
Hello? Yes, can you hear me?
Yeah, please continue.
Okay. So as I said, the trade-off underscores the significance of the macroeconomic modeling in capturing the upstream stages, which if we exclude it, it could adversely impact the embodied water as compared to embodied energy, because embodied water has more higher values downstream, upstream into the 12 different stages. And the results here show a comparison between the direct and indirect components of both embodied energy and water. So the plot here shows that for almost all the materials considered, the direct embodied energy is higher than the direct embodied water. So we use more energy directly while we are producing these materials as opposed to the direct usage of water. The exception here is only for concrete, CMU, and flashing materials. And 9 out of the 14 materials that we considered here had more than 50% direct embodied energy, whereas only 5 materials here had more than 50% direct embodied water. So out of the total embodied water or total embodied energy, we can see how the trade-off lies between different materials. Not all materials have the same embodied energy and embodied water footprints. So this clearly shows that the direct and indirect embodied energy and water components vary significantly for different materials, and therefore it is extremely important for us to consider a disaggregated approach where we don't analyze a building as a whole. Instead, we disaggregate and consider the different materials used for the building, and then combine the results to get the total results for a building level analysis. Moving forward, the plot here shows the proportion of energy-related embodied water. So the energy-related water varies from roughly about 2.5% to 31% of the total embodied water, and aluminum, steel, and plaster materials had the highest share, as you can see here in the plot here. While carpet, paint, and wood had the lowest shares with just 2 to 3%. Concrete and steel, however, had an embodied energy-related embodied water of up to 13 and 27% respectively. And with these two materials being the two most widely used building materials, their share of embodied and energy-related embodied water is extremely significant for an environmentally sustainable built environment. And finally, we can see from this plot here shows a correlation between the embodied energy and the embodied water. Evidently, there is no correlation between the embodied energy and embodied water. So this suggests that a design decision made only based on embodied energy or embodied carbon may conflict with embodied water for some materials. And therefore, it is important for us to improve the production of energy sources, such as electricity, which consumes approximately 52% of the total energy-related embodied water. That translates into 3 to 5% of the total embodied water of a building. So improving the production of these energy sources, and with less water usage, we can translate or remove the 3 to 5% that's being contributed by the energy-related water. And in the United States, about 40 to 50% of the water is consumed by thermoelectric power plant to generate electricity. So we can see how the integrated carbon, energy, and water model signifies the importance of both embodied energy, or embodied carbon for that matter, and embodied water in selecting building materials. And this can help us create a truly sustainable built environment. So any design decisions that's only dependent on embodied energy could impact the embodied water footprint adversely. So with that in mind, now I would like to show you two case studies. One is on vanadium microalloyed steel, rebar and structural steel, and also surface aspect ratio of buildings. So one case study is to look into the material aspect, and the other case study is to look into the design aspect. So these are not just like, I'm trying to show one example from the different material properties or the different design stages that we could possibly consider to reduce these footprints. So vanadium microalloying of steel. So in order to conduct like a life cycle assessment of the vanadium microalloyed steel, our final goal is to come up with an LCA indicator, which is like a global warming potential or carbon dioxide emission. But in order to do that, we need to explore different life cycle inventories. And to utilize these life cycle inventories, we need quantity of different materials. And to get these quantity of different materials, we need to see the design or how we design different buildings. And in order to get the design, we need the material, geometric, and loading properties. So this chart here shows, it's a schematic showing the framework that we use for the vanadium microalloying of steel. So this was divided into 4 different stages. The first stage was the modeling phase, where we had 2 different models. One was the structural model, and the other one was a machine learning model. The structural model had different inputs of the order of materials, geometric, loading, and other site conditions, while the machine learning model had primarily literature data that we got for to see how much vanadium content is required to obtain a particular strength of steel. So the output from the modeling were from both the structural model and the machine learning model were both a function of the yield strength of steel. So from the structural model, we got the total quantity of concrete and steel as a function of yield strength. And from the machine learning model, we got the percentage of vanadium that's required to obtain a particular yield strength. And these two were then combined. We got the material savings, and the savings were combined to integrate it with the life cycle inventories, the existing life cycle inventories. And so for carbon and energy analysis, we use the inventory of carbon and energy for concrete and steel. And for vanadium, we use some literature studies to get that data. So you can actually see here that the vanadium product is primarily obtained as in a secondary form. So therefore, the footprints in terms of carbon and energy is very low for this particular commodity. Only 14% of vanadium is obtained as a primary, in terms of primary production. So finally, once we have the life cycle inventory, then we combine all this to perform an impact assessment to compute the total embodied energy and embodied carbon of using mild steel versus the vanadium high-strength low-alloy steel. And here I'm just showing the model that we prepared using the machine learning. So here we can see how the change in vanadium content influences the yield strength of the steel. So from this plot, we can see that there are three components that primarily impact the yield strength, that is nitrogen, vanadium, and manganese. And the highest values of the yield strength was observed when the vanadium and nitrogen content was maximized, while the yield strength generally increases with increasing manganese content, but only up to a value of about 1.2 weight%. And after that, you can see that's kind of like a threshold value beyond which you can see that the yield strength of steel reduces. So using this model, we obtain like the percentage of vanadium that's required to generate a particular grade of steel. And from the structural modeling side of it, what we did was to break it into two different analyses. One was at the component level, where we looked into different reinforced concrete components like the concrete slab, beams, columns, and footings. And then we moved to a building level analysis where we had a hypothetical building model that was developed. And then we looked into the savings in terms of steel as well as concrete. So the first stage was only looking into the savings in terms of steel. The second was to look into when we reduce the steel values, we also reduce the cross section of the different components, and that would also reduce the concrete content. And similarly, we did a modeling to change the frames from reinforced concrete to steel sections. So here we just had like two different components. One is a steel beam and the other is steel column. So this is just one single example for the component level analysis that we did, where you can see if we improve or if we modify the mild steel to a vanadium high-strength low-alloy steel, we are actually improving or enhancing the compressive strength of the material. And that would directly translate into reducing the total amount of steel required for that particular component. And that could also mean that we are reducing the overall cross-sectional area of the entire column as a whole. And these are some numbers that we obtained for only the frame level analysis. So just to be consistent with the two different models, one for the reinforced concrete and one for the steel section building. Here, the reinforced concrete beam and the reinforced concrete column versus a steel beam and a steel column. So we see that there is a huge difference in the amount of savings with respect to reinforced concrete and steel sections. And one of the reasons for reduced savings in terms of steel is because we have standardized steel sections. So we don't have a lot of choice, even though we are improving or enhancing the strength of the steel materials, we still have to abide by the rules or standard specifications, and they have like standard sections, and we don't have something in between two different sections. So due to that factor, we can see that there is reduced savings in terms of steel sections, but there's more savings in terms of reinforced concrete sections. And for the analysis purpose here, we used Eurocode specifications. And moving to the building level modeling, we modeled 4-story 5x3 bay hypothetical building with reinforced concrete flat slabs, beams, columns, and shear walls were also modeled. And we only changed the frames to steel frames in order to analyze the steel section building. So ETABS software was used to analyze this, and all the standard specifications from Eurocode was used to perform the analysis. And you can see how the how this translates into percentage savings in steel, where the 250 grade is a mild steel that does not use vanadium, or there's 0% vanadium in that grade of steel, whereas 400, 500, and 600 are high-strength low alloy steels that have some amount of vanadium incorporate microalloyed into those steels. And as I mentioned previously, the life cycle inventory that we used here for this study was inventory of carbon and energy, the ICE database. And you can see how the embodied energy and the embodied carbon of rebar or steel is beyond an order of magnitude as compared to the embodied energy and embodied carbon of concrete material. And for the energy and carbon values of vanadium, both from the primary and secondary production of vanadium, we obtained it from digging deep into different literature sources that's listed down here. And we did a weighted average, which was like a process analysis to obtain the average embodied energy and embodied carbon values for vanadium. So once again, it's important to observe that the primary production of vanadium, we have a very high value for embodied energy and embodied carbon, whereas the secondary production, there's reduced amount of embodied energy and embodied carbon for the vanadium production. So the weighted average is more skewed towards the secondary values. That's because 86% of the vanadium, total global vanadium production is due to secondary sources like co-production or as a byproduct in the process of producing vanadium pentoxide. And so from an environmental impact perspective, how would this translate into the environmental aspect? So in 2018, we can see that the global steel production was approximately 1.8 billion tons. And in the same year, 51% of the steel market was consumed by building and infrastructure. And 44% of this number was allocated only for reinforced bars, and 25% was for structural steel sections, and the remainder were for pipes and other steel products. And finally, we can see that the total global carbon emissions reached a value of about 37 gigatons in the year 2017, 2018. So what we did was we used this information and we calculated some numbers to see how much savings we could have had from different regions. Here we considered China, the European Union, and also based on some of the information that we received from China and European Union, we extrapolated the numbers for world as well. So we have what you're seeing here are the numbers that you see at the bottom down here, which is the 2017 carbon savings, which is directly attributed to the vanadium microalloying for different regions. And also the percentage that you see here is the percentage savings with respect to that particular region's carbon emissions. So if we just look at the worldwide emissions, we could have saved up to 136 megatons of carbon if we completely used high-strength low alloy steel, microalloyed using vanadium, as compared to using just mild steel across the world. And those numbers are pretty significant in China because China has the highest production of steel across the globe. More than 50% of the steel that's produced around the world is just from China. And that's why the number from China is pretty high, almost up to 100 megatons. Whereas the value from European Union is pretty significantly low. It's just at 6.6 megatons. So this kind of shows the trade-offs that these values are not consistent or cannot be averaged across the globe. They vary from region to region, and China being a clear outlier as opposed to all the other countries. And that's also owing towards the high production of steel in China. And just to throw some light on advanced high-strength rebars. So in this slide, I just wanted to touch base on the advanced high-strength steel, which has a compressive strength of over 100 KSI or approximately 700 MPa. So the benefits of using this high-strength, advanced high-strength steel is that there's lower percentage of steel that's required for the same amount of loading, and there's reduced member sizes, there's reduced bar sizes that could be used within the component, and also there's more usable space within buildings because we are reducing the size of the components. So this was a study that was conducted in Germany, where on the leftmost diagram here shows a column which is 1.5 by 1.5 meters, and you can see that they use a 500 MPa steel. Whereas when they switch to a high-strength, advanced high-strength steel, which is roughly of the order of 800 MPa, we can see that for the same size, they use reduced number of bars, so there's less congestion within the rebar caging, or we could reduce the overall size of the columns. And that's an actual building, which is in Switzerland. It's the Roche Diagnostics building that was constructed and designed by Fiscus International Engineers. And the specialty of this building is that it doesn't have any beams. It's just V and A-shaped columns, as you can see through these glasses here. And they use 700 MPa rebars. So they are high-strength steel, and you can see that the overall structural framing, they don't have any interior columns, it's just exterior columns and shear walls. That's the lateral load-bearing system there. And there's a lot of space that's available for usage or utility within that particular building. So that's an actual structure that was made using advanced high-strength steel. So with this idea, this slide shows an overview of how the 4 different phases of life cycle assessment framework that I presented at the beginning, it clearly shows how the reduction in embodied energy and carbon could be obtained by microalloying vanadium into steel. And a similar approach may be adopted to efficiently conduct material flow analysis and determine the impact of other waste-derived materials in concrete as well. It's not just limited to vanadium or steel. This analysis could be extended and implemented into other different materials. And moving towards the design aspect of buildings, we can see that we could do a design optimization, and here the example that I'm considering is aspect ratio of buildings. So the design parameter, as I mentioned, the aspect ratio, which is often defined as the ratio between the horizontal and vertical dimension, or between the 2 different horizontal dimensions of a building. And we can see that for the same usable floor area, we can design a building either horizontally or vertically, that is, with different aspect ratios. And this would impact the design of the structure, and in turn, it would impact the quantity of materials, especially concrete. And in this study that I'm going to show you, we tried to examine how aspect ratio may affect the environmental sustainability of a building structure, of a reinforced concrete building structure. So the primary aim here is to assess the impact of the aspect ratio on the use of concrete in its buildings. And to achieve this, firstly, we define the aspect ratio not the usual way. We redefine the aspect ratio rather as surface aspect ratio. And that's primarily to include all the 3 dimensions of a building into one single parameter, which is the surface aspect ratio. So we can now define this aspect ratio as the ratio between the horizontal surface area to the vertical surface area. So now it's a 2D by 2D, 2-dimensional ratio, as opposed to the 1-dimensional ratio that's often described as aspect ratio. And second, we calculate the total quantity of materials, that is primarily steel and concrete in this case, that's required for buildings with different surface aspect ratios. And finally, we try and compare these results for different aspect ratio scenarios. And we discuss the impact of the variation in the usage of quantity, usage and quantity of materials. So as I mentioned previously, we define the aspect ratio, that is the ratio of the total horizontal surface area, which includes all the red regions that you see here, which is nothing but the total usable floor area, with respect to the peripheral vertical surfaces. So for calculation purposes, we used a center-to-center dimension for length, breadth, and height. And as shown in this figure, the horizontal surface area is represented by the floor surfaces, and the vertical surface area is nothing but the total peripheral surface area. So to meet our objective, we need to find a relationship between surface aspect ratio and the total quantity of materials. So for this example, we began by taking an actual 12-story building with a total floor area of approximately 10,600 square meters, assuming that each floor height was about 13 foot. And then we changed the surface aspect ratio by changing the number of floors from 12 to 9, 6, 3, and 1. And in order to compare the quantity of concrete and steel, we kept the total floor area, or the usable floor area within the building, a constant parameter. So this is a flow chart showing our approach. So our approach considered 3 input values here, that is the floor height, the total number of floors, and the total volume of the building. Here, the green box represents the changing variable, and these 2 parameters are kept constant. So the procedure starts by with calculating the total height of the building, followed by the total floor area, which is used to determine the length and breadth of each floor, assuming that here, that's an assumption that we made, which is length is twice the breadth. And then we determine the total horizontal and vertical floor areas to calculate the surface aspect ratio as defined by the formula that's shown here. We then performed a structural analysis using standard loading conditions and calculated the total quantity of materials that was required. We then changed the total number of floors and repeat the entire process for different aspect ratios. So since the floor area is held constant here, so it's for the same floor area, we are varying the height. The horizontal dimension, that is the length and the breadth of the building, are observed to increase with a decrease in the number of floors, which is quite trivial. So to perform the structural analysis, once again, we use the ETABS structural software to perform the superstructural analysis, and RISA Foundation software was used to analyze the substructure. And the loading details are based on the standard loading specifications from the AC7 standard. And the table here just summarizes all the modeling assumptions that we did. So we assumed a 9-inch thick drywall and a 6-inch thick concrete floor slab. The concrete strength was taken as 4 KSI, or roughly 28 to 30 MPa. And the rebar steel that we considered here was 60 KSI, that's roughly 450 MPa. And all the other loading parameters here conform to the AC7. So this slide here presents the 5 different cases that we considered with respect to the superstructure and the substructure models that were prepared, as well as the total number of floors and their respective aspect ratios. And since the aspect ratio would be an inverse function of the total number of floors, we can see as the floor numbers reduce, the surface aspect ratio value increases. And you can also observe, it's not to scale, but you can observe that the individual floor area here is small for the 12-floor structure, whereas the 1-floor structure, it's extravagantly big since we are maintaining the same usable floor area. So coming to the material quantities that were quantified at the end of the analysis, the graph here shows the results obtained after the structural analysis. So from the graph, it may be observed that the quantities of the construction materials decrease as the surface aspect ratio increases, or we could say that as the height reduces, the quantity of materials required also reduces. And the rate of decrease in quantity is observed to be higher for steel than concrete. And also, due to the inverse relationship between the floors and aspect ratio, there is an inverse relationship between the material usage and number of floors. So the results obtained here are quite trivial because as the height of the structure increases, the total gravity load onto the base columns increases, which increases the base shear or the base reaction. That raises the total quantity of steel and concrete required for the individual foundation or individual footings. Further, as the loads are higher on columns that are at the bottom level of a tall building, the size of the columns and as well as the beams increase as we go from top floor to the bottommost floor of a tall building, which tends to increase the total volume and quantity of materials required for each structural element. So the variation or the drop in quantity of concrete and steel is therefore directly dependent on the total load that is transferred to each of these structural members. And one aspect that I would like to focus here is that in the present study, we looked into only sustainability of concrete from a material savings point of view. And even though the preliminary results suggest that the construction of taller buildings may need more quantity of steel and concrete than the horizontal ones, analyzing the sustainability of concrete just based on material quantities may lead to misleading conclusions. Therefore, the sustainability of concrete should be viewed from a more holistic perspective that also includes other factors such as availability of land usage, and the area of permeable surfaces on ground. So for instance, considering all these parameters, a horizontal design of a building may help improve the sustainability of concrete through material savings. However, it may intensify the urban heat island effect. It may also decrease the ground permeability, increasing the probability of flash floods, which is particularly concerning in the cases of radically changing climate conditions. Then availability of land area for horizontal construction is also a challenge, and this may call for a vertical construction. A vertical design, however, may require more concrete, but on the other hand, they offer opportunities of having more permeable and green space on ground that can help control the urban heat island effect, to keep the urban air temperature lower. It may also offer more vegetated ground to soak rainwater and reduce the chances of flash floods. And they also offer parking spaces within the building, and therefore additional land for parking is not required. And also increased green space may also mean increased quality of life. And in general, the amount of roof and wall surface also influences the amount of heating and cooling loads of a building, which consequently would affect the operating energy consumption. Also, please note that in this study, we are not trying to favor a vertical construction over a horizontal construction or a horizontal construction over a vertical construction. It is rather arguing to apply a more holistic perspective to analyze the sustainability of concrete as it relates to individual building designs as well as urban environments. So the idea here is that it is not a one solution problem, it is a multi-objective issue. And from a carbon, energy, water perspective, I would say that the contribution of the embodied carbon of concrete and steel decreases with the increase in surface aspect ratio or with decrease in number of floors. And also the contribution of embodied water of steel decreases with the increase in the surface aspect ratio. And the variation is relatively lower as compared to the embodied carbon. So you can see that there is still a trade-off between even at a building level, there is a trade-off between embodied energy or carbon and embodied water. This figure here presents a comparison of the results with respect to the single-story building. So we are comparing the low to high-rise or low to medium-rise building structures with respect to that one floor structure. So the A plot here shows the variation in the contribution of material quantities for the different aspect ratios that we considered. And we can see that the total quantity of steel significantly reduces as we decrease the number of floors, while the decrease in the quantity of concrete is somewhat lower. And one of the reasons for this could be that the size of the floor slabs is kept constant for all the cases here. And that's primarily due to the limitations that we have with respect to slab thickness reduction, which is owing to the vibration issues that these buildings could face, and that could adversely affect the serviceability of the building structure. The B plot here shows a variation in the total embodied energy, embodied carbon, and embodied water for the different aspect ratios. And once again, it is evident that there is a trade-off between the embodied energy and embodied water. You can see that there's a similar reduction in embodied energy and carbon, but the reduction in embodied water is slightly different, even from a building perspective, as opposed to just at the material level that was presented previously a few slides back. However, all that I presented here may sound cool or may sound advanced, or it sounds like it's implementable. But the problem that we face is that all these concepts are more at a conceptual stage, or more of a hypothetical analysis or a research phase. What's more important for us is to see how we could implement these into recommendations. So with the construction industry that exacts a heavy toll on limited natural resources, leaving a massive carbon footprint that's derived from carbon-intensive nature of the key structural materials like concrete and steel. So an important factor here is to ensure that these research studies reach the public. So it's important for us to ensure that these findings are disseminated to our clients and stakeholders in the form of, publications or presentations and workshops like how we are conducting it today. And engaging the audience by quantifying the benefits in terms of profits. And the profit is not just with respect to cost, but also with respect to energy and other natural resources. And this would translate into unlocking the bigger and a goal in terms of environmental sustainability. And I believe that this engagement is needed for the practical implementation by bringing the implementing agencies or federal agencies, such as government agencies or industry partners, contractors and manufacturers, all of them on board. And also understanding the implication of government policies or federal agency policies is the need of the hour requirement. So just to give you an example of how important federal policies are, circling back to the vanadium project that I was talking about, the left plot here shows the production of high-strength steel in China, and the right plot here shows the savings in carbon emissions. So in 2008, approximately 70% of the steel produced in China were grade 2, which is mild steel. So there is no vanadium in it. However, after the Sichuan earthquake in 2008, China revised their seismic design codes. And what they did was in 2011, they restricted the use of grade 2, which is the mild steel, and increased the high-strength rebar production. And that is reflected with some offset in the year of 2013 in the form of carbon savings. And later in the year 2018, they banned the use of grade 2. So they completely eliminated the production of mild steel and QST steel, which is once again apparent in terms of carbon savings. So we can see after the 2018 implication or change in specification, you can see how there has been savings in terms of carbon emissions. And that's owing to the factor of omitting the mild steel or high carbon steel. Therefore, such implementation strategies could be helpful in achieving our goals, and hopefully with such baby steps, we should be able to touch the carbon neutral goal by the year of 2050. So that kind of brings me to the end of the presentation for today. But before I end, just for 5 minutes, I wanted to just throw light on this particular paper that I read recently. It's on the structural design of the urban Sequoia Tower. And I think it's a great platform here to kind of discuss this. And for all the people who are interested in, structural design and sustainable structural design, this could be an inspiration. So this paper, or this concept rather, was developed by this company called Skidmore, Owings Merrill. And for those of you who are not aware of this company, it's a US-based architectural and structural company, and they are responsible for the structural design of the Terminal 2 of Bangalore Airport as well. So if you've seen the Bangalore Airport recently, it was one of the largest airport terminal that received a pre-LEED certification, and that was owing to the fact that it was a sustainable construction. So this particular urban Sequoia Tower concept, the motivation for this concept was from the fact that what if buildings could act like trees? We are cutting down trees, but then we are building buildings there. So what if we could replace the trees with buildings? And the notion here is to see whether buildings could capture carbon, it could purify the air, or it could regenerate the entire environment which was existing before the building was constructed. So I'm not going to get into the details of this, but just wanted to show like the structural system that they came up with, which is a prefabricated modular construction. So the plan here shows the different modules that they prefabricate and transport it to the site, and then they kind of integrate this on site to form an entire floor system. So the left figure here shows the floor system, which uses these different materials. Once again, I'm just going to rush through the different materials that they use. But basically, the materials that they use are recycled steel and low carbon concrete. And they also use the direct air capture concept, which kind of absorbs carbon dioxide from atmosphere, and it's absorbed into the building, and then it is transferred into the ground for carbon capture and carbon storage. And they also used algae-based concrete masonry unit for formwork, which could be permanent formworks there, and that's a biocement. And they performed a comparative case study. So that's an actual building that's existing in San Francisco. That's the benchmark tower that they took, which is a 42-story, 420-foot tall structure. And they came up with a parallel urban Sequoia Tower with the floor plan as shown in the figure right here, where the total height of the structure and the total floor area of the structure was kept the same. And they tried to do a life cycle assessment to see what's the total embodied carbon in these two buildings. And so for the benchmark tower, they observed that roughly about 9,500 to 11,700 tons of carbon dioxide is the embodied carbon dioxide for the benchmark tower. Whereas by using the urban Sequoia Tower concept, they found that that concept would have only 2,800 to 3,400 tons of embodied carbon, which is clearly a 70% reduction in embodied carbon. So that's like we are starting the entire construction process with 70% reduction in its initial embodied carbon phase. And also they predict that if everything works well, in a life cycle of or lifespan of 60 years for that particular building, roughly 39,000 tons of carbon dioxide could be saved from just one single building. And that's owing to the fact of the algae-based bioconcrete, which contributes to 25% of the savings, and the direct air capture contributes to 75% of this 39,000 tons life cycle saving. And a path forward that they show is not just focusing on net zero, but also to move net negative carbon. So it's not just to bring back the emitted carbon, but also to remove the carbon from the atmosphere, additional carbon, and move it down into the ground for a carbon storage. So the captured carbon and the biomass could be used for producing biomaterials for other infrastructure like roads and pavements and pipes. And you could also extend this concept from buildings to cities. So you can expand this concept not just for a building infrastructure, it could also be for generating parks or other commercial structures as well. So some of the key takeaways from this paper that I personally felt was the sustainable design thinking of going not just to net zero, but also to push this forward to net negative. And they also used, or they came up with concepts that are ready to use technologies. So we don't have to really come up with these technologies, the algae-based concrete or the low carbon concrete, they all exist out there. It's just a matter of time to be commercialized. And also this could be scaled, not just for a high rise, it could go down to a low rise building or a single story residential building as well. And we can see that they used 5 different concepts here, which is like improving the existing materials, optimizing the structural design, biomass concepts, integrating biomaterials, the concept of carbon capture. Each of these are standalone solutions for sustainability, but they kind of integrated all of these solutions into one single building, which according to them, if we can achieve this strategy, you could save 650 tons of carbon every single year from that one single building, which actually translates to 31,500 full-grown trees each year. That's almost bringing back the cut down forests or deforestation. So I just wanted to end with this note for all the interested people who want to maybe explore more. Feel free to go online and search about or read more about the urban sequoia tower. So with that, I would like to thank you all for your patient listening, and I'll be happy to take any questions that you may have.
Dear participants, if you have any questions, please, this is the time for the questions, any queries regarding this.
And also, if you would like to learn more about this, please feel free to reach out to me via my email, and I can share with you some of the resources which kind of describes the
Pranav, can you
models.
post your address or email ID on the screen so that the participants, anybody is interested, they can interact with you?
Sure. I can maybe put it in the chat box.
Can you display in the screen?
Just a second.
The link also blog. In the meantime, can I ask one question? Now, as you are talking mostly about the carbon footprint, climate change, life cycle energy, sustainability. Now we are having in most of the Indian cities, like for example, take Bangalore, we have enough number of rains, but when it comes to summer, we have a lot of problems. And everybody say it is due to the development, urban sprawl, urban growth. So in sustainability related to that, how we can improve the situation by using the sustainable approaches or sustainability concept? Can you throw light on that?
Yes, for sure. I think we should look at it from 2 different angles. One is moving forward from today, and one is to look at what we have already done. So a large amount of what we are facing today is not what is lying in future. It's because of what's already been happening there. So with that perspective, I think it is important to see how the existing structures or the existing infrastructure could be modified in terms of providing better drainage system or providing better rainwater harvesting and water capture systems or carbon capture systems, etc. So I think the focus should be more like what I've presented today is more of a future perspective, or how we could come up with new strategies that could be implemented for future. But the question that you have asked me, I think it lies primarily with what's there today or the infrastructure that's existing today. So maybe coming up with strategies that could absorb or capture water and carbon could help us reduce the problems that we face in terms of urban sprawl. The issue is urbanization and how far are we expanding. So if we are expanding vertically, then we are having more population density within the urban spaces, and that could create a lot of these issues. But expanding more horizontally as the cities grow, that could help in slightly reducing these impacts.
Okay, thank you. You haven't shown your mail ID
Yeah,
and all on the screen.
You can also type it in the chat box, Pranav.
Yeah, I can just.
Any other questions from any of the participants?
Pranav,
Hi, sir.
Pranav Shivanna here.
Hello, sir.
Yeah. My question is, you have talked about the carbon reduction and the usage of some other materials and all.
Mhm.
But what about the cost and all? Is it come down when it comes to utilization of, you are telling vanadium, like steel and other things and all?
Oh yes, absolutely, absolutely. In terms of cost, so we did not perform a separate cost analysis, but clearly there is a I won't say a cost reduction, but there is no increase or significant increase in terms of cost, and that's because we are having plants that are capable of taking these processes or microalloying, because high strength low alloy steel is not a new concept. It's been there around for like 3 to 4 decades, and so all the plants across the globe are capable of taking this or producing this type of materials, and therefore the production stage does not have any cost implications. The issue lies with how the production of the vanadium is attributed to. So as I showed in the slide, about 86% is a co-product. So since it's a co-product, it's a byproduct, or it's a waste material that's coming from other industries. So there is absolutely no cost involved in that, and that kind of reduces the overall cost implications. That's just with respect to the vanadium example that I showed.
So thank you, Pranav. The other thing is, like if it is quite cost effective, why these construction companies are not make use of these things and all? Is there any production as far as India is considered relating to this particular vanadium bearing steel or titanium bearing steel?
I still feel that there is increased use of vanadium based steel even in India, because the high strength low alloy steel or any of the high strength steel that we use even in India, they are all different alloys, but it might be vanadium or it could be niobium based steel, etc. But the concept is already in there. It's just about how we attribute the life cycle analysis. So that was a concept that not many industry folks or the manufacturers, the plant people don't look into, because they are more interested about the production phase or how just the upstream material production details. So they don't look into how the design phase is going to happen. But what we are trying to see or look into was to kind of consolidate all the different phases by seeing the production or the manufacturer, then combining it with the architect, the design phase, and also the use phase. So when we combine all these different stages, we see the benefits in terms of environmental sustainability. So even at manufacturer level, they do account for some level of life cycle assessment as of today. But yeah, we can still improve this, but that just depends upon the government policies. As I mentioned at the end, all these can only come into light if the government policies or other local state agencies and city councils adopt these policies. And if you see the design codes don't really change every year. They are updated or modified like 5 years or 10 years down the line. So if they are modified after 10 years, all the development within that in that 10 years will be reflected only after the new code specifications are generated. So those are some limitations with respect to the design aspect that we observed.
Yeah, thank you, Pranav, because that is only the issue here, because manufacturers are not known all these things and all. They always think of, like profit wise.
Absolutely.
They have to change the technology. Once they have been enlightened regarding how they are going benefited, how the life cycle of the building is going to be improved. So then only I think they'll come forward to change and use these sort of things and all for making the new materials which can be used and to reduce the impact of this carbon on this globe.
Absolutely.
So thank you, Pranav. You are absolutely correct, because the government has to take very much initiative to do all these things and all. Otherwise, no, the way we are facing in Bangalore, the water problems and all. Though the water is rainfall is so almost same every year, maybe little less, but still we are finding so much of difficulty in meeting the demand of water in this Bangalore. Right? Thank you, Pranav.
Sure,
Nice
thanks.
to see you after a long time. And when is your? You have any plans to come to Bangalore?
Not immediately, sir. Probably after a year, maybe.
Okay, okay. So okay, take care. Bye. Thank you so
Sure.
much.
Thank you, sir.
Yeah.
It's very late in the night. I think it's almost 12. I think, Pranav, for you there, 12 a.m.
It's 2 a.m. sir.
2 a.m. Oh, thank you very much. You are there. I think our participants should definitely appreciate yours. Thank you. Madam, Tamil Selvi, madam, please.
Yes, sir. Can you hear me, sir? Hello.
Continue,
Can you hear
madam.
me,
You
sir?
carry on, madam.
Dr. Pranav, it's a great lecture actually. Really, it was a fruitful session. What you're doing to the sustainable environment, it's something great actually with your technical expertise. So really wanted to continue this kind of lectures for our students also. Related to the concrete, if any researches is available, please share it to that next time. Related to
Sure,
concrete,
absolutely.
can we make it sustainable? So this will be very helpful for us. See, whatever today you have presented to observe, and the process itself is taking time for us. See, that kind of technical knowledge that you are in, I'm really happy to see that. And really, we wanted to, it's really encouraging for as a teacher to be more having a knowledge in technical field. So this is
and I
what.
also
Yeah,
agree
we
that
need
the details were a lot in the slides, and therefore, like, if anybody wants to know more details, I can share the resources, and feel free to contact me anytime.
Yeah, that will be very helpful. Yeah, yeah. Thank you so much. So it's a time for the vote of thanks. Good morning, everyone. And I really thank today's speaker, esteemed speaker, our alumni, Dr. Pranav sir. Thank you so much. And this is Tamil Selvi, Assistant Professor in the Department of Civil Engineering, respected faculty members and esteemed guests. On behalf of Saram VIT and Department of Civil Engineering, it's my honor and privilege to extend the heartfelt gratitude for all your presence and participation in the special occasion of 5-day FTB on sustainable construction materials, practices, and technologies. I would like to begin by expressing our deepest appreciation to all our distinguished speakers for gracing occasions in the past days and sharing their profound insights on sustainable construction materials, practices, and technologies. Special thanks to our esteemed management for their unwavering support. Without this, this event won't be successful. I extend our sincere gratitude to our beloved principal, Professor Rakesh SG, sir, for his guidance and encouragement in leadership. A special mention goes to our head of the department, Dr. Ravikumar H, Associate Professor, for his leadership and also his support. And next, I wanted to express my sincere gratitude to our Dr. Shivana sir and Sri KVR Prasad sir, whose assistance was instrumental in securing the valuable presence of our esteemed speakers for the sessions. And a great special thanks to Dr. Jagdish Kumar sir for being a great support related to the media. And my sincere thanks to Ms. Anita J for her tireless efforts in ensuring the success of this occasion. I want to thank Dr. Pradeepa for her constant support in doing all this process. I extend my appreciation to our core team members, Srimati Ramya, Srimati Bhavya, Srimati Vaishnavi, Srimati Shubhadra, and Sriram Mustapure for their unwavering commitment to ensuring the success of this great occasion. And also, I want to extend my appreciation to all the staff members in my department for their support. Dear participants, thank you so much for your keen interest and positive attitude towards sustainable technology during this event. Your time and contributions, it is really invaluable to us. I also extend my heartfelt gratitude to the faculties from our college for their patience, presence, and active participation inspirations throughout the events. Thank you all once again. Thank you so much.
Selvi
you.
madam, whether Anita ma'am is there?
Yes,
Anita
sir.
ma'am,
Yes, sir. Yes, sir.
can
I'm
we
there.
ask any one or two participant to share their feedback, madam? If possible, can you ask them, madam? Can they speak?
Yeah,
Who have
sure.
attended 5-day? Can you just ask? I think it already vote of thanks is done. But can we ask anyone to present? If anybody wants to tell their feedback, we can ask them online, no?
Yeah, sure, sir.
Can
Dear,
you ask, madam?
dear participants, if any of you have any questions or any feedback to give, please feel free to unmute yourself and give your valuable feedback.
Can they unmute on their own, madam? Whether setting allows them
Yes,
to
sir.
unmute?
Yes, sir. They are allowed to unmute.
We request any one or two participants to kindly unmute and please say a few words about this workshop, about this. Whatever your feedback is very valuable to us. Can anybody, other than our department faculty?
Dear
I
participants,
think there is
your,
one 7 Vinayaka. I am seeing 7 Vinayaka person for last 5 days. Mr. Vinayaka sir, can you please unmute and you can say your feedback? And also Dr. Velakkaila Gajendra is there. If he is there, he can also speak.
dear participants, your feedback is important to us.
Associate Professor, Department of Civil Engineering, Swarnandra College of Engineering Technology in Andhra Pradesh. So from the day 1, the topic started, and day 5, 5th day. So each and every topic will be helpful for the practicing engineers and as well as the faculty who are going to be attending. Very important topics they delivered, and we got sort of a lot of information and valuable information from all the topics what is going to be given in the 5 days. It is a sustainable environment because this is a need of the hour for the civil engineers. So day 1 to day 5, all we organized very well with respect to that the design aspect, and with respect to that the software, how the modeling has done is given the given in all aspects. So I hope this FDP program giving all the details of the sustainability in all respects. So thank you for giving the opportunity for the organizers, and it's well organized by the SRMAIT College of Engineering Technology. Thank you.
Thank you, Dr. Velakkaila Gajendra. I am happy to share that I am the classmate of Dr. Velakkaila Gajendra in MTech. Thank you very much, sir, for joining.
Thank you, sir, for your valuable feedback. Anyone else, if you are willing to give the feedback, you can unmute yourself.
Dr. Gajendra, you can mute your mic. Dr. Gajendra, you can mute your mic. Okay, madam. If nobody else is joining, we have to take another group photo, madam, again.
No, sir. That's We have
No
taken-
need, no? Okay.
Thank you everyone for joining us for today's session and through the entire past week. We thank each and every participant who joined, who connected with us for the past 5 days. It was a pleasure having you. Special thanks goes to Mr. Pranav for joining us in today's session. It was great seeing you after such a long time, and your presentation was really informative. And thank you for a lovely session. Thank you. one
Madam, we want Dr. Pranav to be here offline, not online. You ask that, madam. Anyhow, thank you, Dr. Pranav, from all the Department of Civil Engineering. It was very nice listening to you. Every time you speak, your lecture will be very fresh, new, and so many new things you will add. Really happy.
Thank you, sir.
Okay, madam. We from all the department side, we thank Professor Anita, who has conducted this program very nicely.
Thank you.
I think H1 sir is not there. On behalf of him also, I'll be telling from all of our team, thanks to you, ma'am.
Thank you, sir.
Okay, madam, can we all leave now?
Yes, sir.
Thank you.